Okay, let's take a look at the suggested practice problems from the last day. All right, so on page 525, number 44, says you and some classmates read the record for the speed of a pitch baseball is 46 meters per second. You want to know how fast your school star pitcher could throw. Not having a radar gun, you use the concepts you've learned in physics class. You make a pendulum with a rope in a small box lined with a thick layer of soft clay so that the baseball would stick inside. You draw a large protractor on a piece of paper and you place it at the top so that one of the students can read the maximum height, the maximum angle at the rope when the pendulum swings up. The rope is 0.955 meters long. The box with the clay has a mass of 5.64 kilograms. The baseball a mass of 3.5 kilograms. Your pitcher throws a fastball into the box, it sticks, the students record the angle to be 20 degrees. This would actually have been our lab if we were still in school. So, here's the box. Now it's lined with clay because the baseball needs to stick. In all of these questions, in the collision, the two objects need to stick together. In class, if we were doing this, it wouldn't be a box lined with clay, it'd be a Velcro target, and the baseball would actually be a tennis ball. Okay, so the baseball's being thrown with some VI that we don't know. The VI of the pendulum is initially 0. After the collision, the baseball is stuck inside the box, and the whole thing swings up. And the height to which it swings up, we don't know. So we don't know what this H is. But because of a handy-dandy protractor that we have up here, we can see that the angle is 20 degrees. Okay, so there are three parts to the problem, but two, like conservation of momentum and energy. Here's the collision, so you're going to use momentum. And this is where there's a change in height, change in speed, so you're going to use energy. You're looking for the initial velocity of the baseball, so this is going to be your last step. You're going to have to start up here. We always call the lowest part, we say the height down there is 0. And it's going to swing up until it stops, so the speed up here is 0. But we don't know this height. So it's connected to that example problem I did with you the other day. You can find the height by creating a right angle triangle here, calling this side of the triangle y, and in the question it tells us the length of the pendulum is 0.955 or 995? 955 meters. So using cosine, we can find y. So cos of 20 is equal to the adjacent y over the hypotenuse, 955 meters. So we can get our y to be 0.8974 meters. Okay, so that means the rest of the rope is our HF. So our HF will be 0.955, our height, minus the 0.8974 meters. And so our HF is going to be 0.0576 meters. And now we can use this in our energy. Okay? So 1/2 mv initial squared, mgh initial, I'm not going to have anywhere close to the room for the whole equation. 1/2 kx initial squared is equal to 1/2 mv final squared, mgh final, 1/2 kx final squared plus E lost. And we said the other day, no E lost with pendulums, and there's no spring here. At the bottom, it has some speed because it's about to swing up, but no height. At the top, it doesn't have a speed, but it does have a height. So we have 1/2 mv initial squared is equal to mgh final. The mass at the bottom as it's about to swing up is the pendulum and the ball, and the mass at the top is also the pendulum and the ball. So the masses cancel, and you're solving for this v. So v initial squared is equal to 2GHF. So 2 times 9.81 meters per second squared times that 0.0576 meters that you just found. Don't forget to take the square root, and when you do, you get 1.06 meters per second. If you had 1.13 there, you just forgot to take the square root. So this speed, the speed with which it initially begins to swing up, is the speed right after the collision. It's the v final in the collision. So m of the ball, v of the ball initial, plus m of the pendulum, v of the pendulum initial, is equal to m of the ball plus m of the pendulum, v final. And this is your v final. Okay, so pendulum isn't moving to begin with, so v of the ball initial will equal m of the ball plus m of the pendulum, v final, divided by m of the ball. So ball's m was 0.35 kilograms. Pendulum's m was 5.64 kilograms. Times this 1.06. There are more decimals than that. I kept them in my calculator. I just didn't keep them. Write them down here. And when you do this, you get a v of the ball initial to be 18.19 meters per second. Okay, so that's what your star baseball player can throw. Number 44. All right, number 45. Number 45 is a boulder up here in the top of a hill. And then there's this ice fishing shack down here. So one starry night when the boulder's lonely, it rolls down the hill in search of friends, and it smucks into the ice fishing shack, which of course, shack isn't moving to start with. And after the boulder smucks into it, the boulder and the shack are connected, and they slide along the ice until friction eventually brings them to a stop out here. Okay, so this time there are 3 parts. There's a change in height, change in speed, so this you're going to use energy. There's a collision right here, so you're going to use momentum. And then they slide along the ice until they stop, so you have to use energy again. Okay, so 3 sections. In our givens, it tells us the mass of the boulder is 55.6 kilograms. And its initial velocity is 0. And it tells us the height here is 14.6 meters. Okay, so we have a height, which means we can start here. A little bit. They also tell us the mass of the shack is 204 kilograms. And they tell us the coefficient here is 0.392. And the question is, how far do the shack boulders slide after the collision? Okay, so we're going to start with energy. 1/2 mv initial squared, mgh initial, 1/2 kx initial squared equals 1/2 mv final squared, mgh final, 1/2 kx final squared plus E loss. The boulder is rolling down the hill, and rolling there's hardly ever any friction. There is no spring on this boulder. At the top, it's stationary before it starts to roll, and at the bottom there is no height. So it's mgh initial equals 1/2 mv final squared. In this case, the 2 m's are just the boulder. They cancel. And we're looking for v final, so v final squared will be 2gh initial. So 2 times 9.81 meters per second squared times the 14.6 meters Remember, that's a v squared, so you have to take the square root. And when you do, you get 16.96. No, excuse me, 16.